Teams don't coopera. Okay, we're being recorded. Okay, let's resume. So we were looking at this image, and the title of the slide, orbit determination, may be a little bit of an abuse. We're not doing actual orbit determination rather than representation, maybe. But so as I was saying, the XYZ Cartesian coordinates representation of the position of the satellite, it's definitely of importance, and that's you can have ways to measure directly position of your satellite from the ground. So that may be actually the information that you have. But for many reasons, it is convenient to represent an orbit and then eventually the position of the satellite on that orbit using, at least in the ideal case where we have Keplerian acceleration only, using what are called orbital parameters. So I'm sure you may have heard of them, or you're very familiar with them. A semi-major axis is what we just looked at, has to do with the size of the orbit. Eccentricity is the shape of the orbit. And then we have the three angles: inclination, argument of perigee, and right ascension of the ascending node, that tell you how the orbit is oriented in space. The I, inclination, and omega, big omega, they tell you how the plane is oriented of the orbit. And then the last one, little omega, tells you in that plane which way the line of apse, the one connecting apogee and perigee, which way it's pointing. Now, we have seen other angles, and so the way that those three angles are defined is you start from the z direction and you perform a rotation from the x ECI axis, the vernal equinox direction, into the line of nodes through an angle capital omega, which is the right ascension of the ascending node, because that would be the node, the point in which the satellite crosses the equatorial plane of the Earth, ascending, so going up towards north. That's what ascending means. And so we have that first rotation. Then we would have a second rotation about the line of nodes through the angle I, inclination, that basically takes the z direction and it moves it into the direction of the angular momentum of the orbit. Remember, angular momentum is cross product of position and velocity. So it's a direction that is normal to the orbital plane. And then finally, about the h-axis, which is the new z and the final z really, you perform a rotation of an angle little omega, or argument of perigee, and that will give you the final direction of the perigee, which is also the direction of the vector E, the eccentricity vector, okay? So since we've seen other angles, what kind of sequence is this? Asking a question to anyone who wants to respond. This is another angle sequence. It's three angles. I've done it with simple rotations. So what kind of sequence is this? This is not a 3-2-1. Any ideas?
3-1-3.
It's a 3-1-3, right? First axis is a z, then you have an intermediate x, because you went from x to this line of nodes, which would be the x prime, and then you rotate about that one, so it's a 1 rotation, type 1, and then the final one is about a new z-axis, so it's a 3-1-3 rotation. And then, so with the A, you have defined, basically, I'm going back a few slides, with A and E, you define this, how it looks like, okay? If you look at the orbit from above, if you like, from the angular momentum perspective, the shape and the size. With the three other angles that I just defined, you tell me how it's oriented in space, and now you have this kind of a track defined in space, and your satellite just keeps moving on it. And so the knee or theta, the true anomaly, is what really tells you the position on that orbit measured from the perigee direction, okay? Now, in the ideal world, the first 5 of these orbital parameters remain constant. Semi-major axis doesn't change, eccentricity, inclination, little omega and capital omega don't change. The only thing that changes is the position on the orbit. And this is true if it wasn't that the planet is not a sphere, the mass is not uniformly distributed. We may have drag if you are in low Earth orbit. We may have attraction from the moon, which we do, So there's all sorts of perturbations that actually make these orbital parameters, the first 5 as well, change. And as everything that we have seen for attitude, these perturbations could be bad, a disturbance, but they can be exploited. So again, this goes a little bit beyond the topic of the class. But for example, the oblateness of the planet at the poles, what we call J2, the fact that the Earth is a little bit like a ball that is been squeezed at the poles, north and south, creates a precession in the right ascension of the ascending node. So your orbital plane rotates, the big omega changes. And that effect is a disturbance, but it's also exploited for sun-synchronous orbits. So you put your satellite at the right inclination and right altitude, that omega changes, the RAN changes, and it can change at the same speed as the Earth goes around the sun. And so you can actually have an orbit that is entirely facing the sun. That's why it's called sun-synchronous. You synchronize that with the sun, and that's a purely free effect due to J2. And so that's a disturbance that is actually exploited. So as in everything, there can be disturbances or effects that we can exploit. But anyways, let's see. Well, this is just looking at some of the orbital parameters from above. So look, put yourself into here, the top of the arrow H, and look down. This is what you see. You will see the x-axis of ECI. The direction of perigee is this way, the line of nodes, and this is a position vector of your satellite. And you have these 3 angles here. Now, a nice change of coordinates. How do you go from, for example, orbital parameters to Cartesian coordinates? Well, you know that in the orbital plane, that's why I call these variables OP, you have the following. The x and y in the orbital plane are given by r cosine of theta and r sine of theta, or me, if you like. So if I go back to this image, if I use the direction of perigee, and well, they seem to be at 90 degrees in this image, but they don't have to be. So forget about this x-axis. In general, this is not the case that the perigee direction is a 90 degree with that. Actually, let's see. Yeah, no. So the perifocal or orbital reference would be the direction of the line of ups, the normal to the orbital plane, and then the cross product of the two. So you would have a y-axis that is pointing up on this image. And so in that x and y, the projection would be r cosine of theta and r sine of theta, nothing special, and no z, of course. There's no projection of the position of the satellite in the direction of the angular momentum. And so once you have these coordinates, all you have to do to bring it into actual x, y, and z in ECI is apply the rotation matrix given by your 313 ordered angle rotation. So you can go back to those images that I shared, and you can easily construct the rotation matrix that goes from these coordinates to the ECI coordinates. And then if you want velocity, well, you would have to, of course, take the time derivative of everything here. And so here you would have, lots of ugly functions with sines and cosines. But you could do that from here, or if you have the velocity already measured, which is probably something you do have, well, very similar transformation. Okay, and then things to notice are that there are expressions for the velocity in the orbital basis without demonstration. They can be expressed as the following functions: square root of mu over p that multiplies the sine of theta with a minus for the x dot component, and for the y dot is minus mu over p e plus cosine of theta. So yeah. So this is the way to go from one to the other. And of course, you can do the opposite as well. As I said, perturbations are a reality. Most important ones discuss. We just talked about the oblateness, J2. It changes mainly the big omega, but also the little omega. It's a little less interesting, but it is definitely there. Atmospheric drag, it will reduce your eccentricity and same major axis over time, but that's only valid if you are in Earth's atmosphere, so low Earth orbit. Above 800 kilometers or so, it becomes less important, and the solar radiation pressure becomes more important. If you have reflective surfaces of on your satellite, eventually the force that is coming from the photons reflecting on the surface can have an effect on your orbit. And then, of course, three-body problem. You have attraction from the moon and the sun, and so those can affect your satellite. As I said before, sun-synchronous orbits are an application of the J2 perturbation. For example, if you put your satellite about 90 degrees inclination, you will be able to actually never be in eclipse. Now, there are differential equations for the orbital parameters that model all these different perturbations, and they're called Gauss variational equations, and I'm sure you may be familiar with those. But in other words, you go back here, and these first five are not constant anymore. You have actual differential equations, A dot, E dot, etc., that tell you how the J2 effect, the drag, etc., can have an impact on the change of these orbital parameters. So we still like to use the orbital parameters. It's just that we don't talk about them as constants anymore. We imagine that these orbits is morphing in time due to the perturbations, but we still imagine at any given time a frozen orbit that has a certain A, E, I, lowercase omega, capital omega, and it's just that they change instantaneously. Okay? Questions? No questions. This is probably something that you already know a lot. And even better than I do. So that's pretty much it in terms of the refresher on orbital perturbations. Since we talked about orbits, though, I really want to go back to, let me close this homework here. To our final assignment, okay? It shows you that there is a block that simulates in the main model. There is this block that simulates orbital mechanics, and out of it I create a desired orientation and a desired omega, and we'll see what they are. But one thing that I could give you to start working on as well, since time is of the essence for a class this short, is this very difficult function here. Okay, so one thing that you can start coding while you're working on your homework one is Keplerian dynamics. Very simple. We don't have perturbations for now. Maybe we can later, but basically the acceleration of gravity around the planet, so that you can integrate in X, Y, and Z the orbit of a satellite. Okay, mu is a constant. And now I am giving initial conditions, and these are given into an initialized file, which is this one. All right, so this comes back. There's of course more stuff than what I showed you yesterday. Let's see. Again, we're not using this for now. If we're talking about orbits, forget about all this stuff. This has to do with the attitude. So let's focus on the orbit part for the time being. So I have this initialized file that gives you the constant of gravity, the mass of the Earth, it is what it is. The mass of the satellite, it's kind of pointless, but I still have it, 1,000 kilograms. If you think about it, compared to 10 to the 24th. It's really nothing, but still, I give an accurate estimation of mu, but if I remove M2 here, it's not going to change substantially. And so I have these initial conditions. And I think we can stick to these. You've seen the plots that I showed you the first time we met when I ran this model. They correspond to an elliptical orbit. I just chose these initial conditions. And so you may need, probably not, but you may need to transform them into orbital parameters. And if that's the case, there are expressions out there that do it for you. And so these are the ones that are coded here. So this is on video, you can use them if it's needed, but the bottom line is that this is obviously the definition of angular momentum. It's the cross product of your position and velocity, and this will remain a constant vector because this is a Keplerian orbit. The eccentricity is the cross product of velocity and angular momentum divided by mu minus the vector of the position normalized. And this is constant. So you can do this with any velocity and any position along the orbit. It will still give you the same vector because this is a Keplerian orbit. So no matter where you do it, it's going to work. And this is just a norm of eccentricity. This is the position of perigee, position of apogee. Nothing special. Same major axis is the position of perigee and apogee divided by 2, obviously, because of geometry. And then the Kepler's law that gives me the orbital period. So I go through all this pain. Why? Because actually I want the orbital period. And so the orbital period requires me to compute the same major axis. To get the same major axis, I needed RP and RA. To get RP and RA, I needed H and I needed E. And so, you can imagine how, and I'm sure this is not the only way, but this is one way to compute the orbital period. So these lines of code are not computing all the orbital parameters. They're computing eccentricity and same major axis. I'm not computing the theta, the true anomaly. I'm not computing the 3 other angles, inclination, ran, inclination, and argument of perigee, but you could. Most likely they're not needed for this assignment, but the reason why I'm computing TE is because that's the final time for my simulation. I'm just, spending some time giving you a little bit of an introduction about what it is that is expected. Then, let's see what we have. We're going to have, so H, the angular momentum vector, is also needed. This is the position and velocity because I integrate the orbit. And so what I spit out here is in Cartesian coordinates, position and velocity. And then I am generating here the desired orientation. So for this assignment, the desired orientation will be being aligned with LDLH. The LDLH that I have introduced today. So this function here takes it into as an input the orbital information, so position and velocity, everything, the angular momentum of the orbit, which is a vector, and the old desired quaternion. So the one computed at the previous time step. If I go back here, there is a memory block here, initialized to the 0001 quaternion that feeds back the previously computed quaternion, desired quaternion. So what's happening in here? I initialize the quaternion to be 1000. Notice here that the 1 is actually in the first component because I think this function that follows is actually doing that. It's as I told you at some point yesterday, I think, some use the different definition of quaternions where the scalar part is the first element of the matrix, but it doesn't matter. As long as you know it, you can move things around. But that's what this function is doing. And this is the this is the DCM to quaternion mine function that I gave you, what comes after. It's the code taken from that. But what I'm doing is these first initial lines is the following. Oops. I'm computing, I will probably need my paper here in a second, but the first instruction is taking orb 1, 2, 3, and it's normalizing that. That is the position vector, because orb is a vector of 6 components, position and velocity. The position vector, it's normalized, so it's now a unit vector, and it's pointing towards the planet because I have a minus. So that's the third axis of the LVLH that I've defined before, the airplane-like LVLH, the one with the Z pointing down. And I call it A3, axis 3. And then axis 2 is minus the direction of the, of course, the unit vector in the direction of H. So it's pointing opposite to H. It's the pitch axis. So this is the yaw, this is the pitch, and then you cross the two and you get the roll axis. Now, the direction cosine matrix that goes from this LVLH basis that I've just defined and ECI, well, we talked about DCM at the beginning. You take the direction of those vectors, because you actually take those vectors and you put them into a matrix. In this case, it's transposed. Go back to what I quickly introduced, the two reference frames, and I projected the unit vectors into the other unit vectors, and that's the definition of DCI. I'm sorry, of DCM. So let me just sketch something here. Stop that and switch camera. So this is what I'm doing. Let's see. Planet, ECI, X, Y, and Z. You have your orbit around the planet, whatever that is. And at any position on the orbit, I have in that function the position vector r. So your A3 is the unit vector that points in this direction. Now the orbit is probably running in this, it may be ascending or descending, prograde or retrograde, but let's say that it's traveling in this direction, so the angular momentum would be pointing this way, kind of north, okay? And then A2, I think it's called, yeah, A2 instead will be pointing exactly the opposite direction. And then you complete the basis crossing the two. This is your A1. And remember, this is what you would call for an aircraft, you call this the roll axis. This is what you call the pitch axis. And this is what you call the yaw axis. Okay? So I'm computing these unit vectors, and by performing the operation that I showed you, I compute them as projected in ECI, because the R vector was expressed in ECI. Okay? The H vector is expressed in ECI. So when I put together DCM, it's the DCM that goes from LVLH to ECI, and it's let's see, it's yeah, it's A1, A2, A3. It's a matrix with those unit vectors put together in this way. So is this making sense? So okay. The next, so I have this function that does that. Let me save it. Okay, share again. So now you're seeing my screen again, and so now I have a DCM. remember I gave you the function that goes from DCM to Quaternion? Well, that's exactly what's happening here. So this is just a copy paste of that aerospace toolbox function that I shared with you. All right. So that's just coming from there. Now, our definition of quaternion is actually different from this one. We have the scalar part being the last one. So I take whatever this function has, these lines of code have done, and I swap the order. So, well, rather than swapping, I take the last element and I put it as the first one and then shift everything else. And so I'm reordering things. Okay. So this is your desired quaternion, because this is what this function is generating. Remember, it's generating a desired quaternion. So I want, this will be your assignment, I want my spacecraft to point its body axis always as LVLH axis. So one of the body axes will be pointing down to the Earth. One of the body axes will be pointing normal to the orbital plane, and then the other one has no choice because it's a cross product of the two. So that would be my desired orientation at all time. And so I am, in this function, defining in terms of quaternion and angular velocity, what is that orientation. Now this line here, it's comparing the old quaternion with the current one. So the one that was computed at the previous time step. And if the dot product of the two is negative, you change the sign to the desired one. Because otherwise you're going to end up with a huge problem of commanding the same rotation but going 2 pi the other way, and that's definitely not a good thing to do. So it's just a sanity check to make sure that you're not, because this may happen from this function, you're not commanding all of a sudden, before you were commanding, okay, rotate about this axis 5 degrees, and then the next step is rotate about this axis 355 degrees, and you go all around to obtain the same orientation. That's it. So that's basically what this is preventing, okay? And the desired angular velocity. So if I want my spacecraft to move as LVLH, well, the desired angular velocity is quite easily the angular velocity of the orbit. Do we agree with that? It's nothing more than the angular velocity of the orbit. The LVLH that I've defined goes with the orbit, and so it's rotating at the same rate as the satellite is rotating about the orbit, and so it's defined as the norm of h over the norm of the position in the direction. So it's h over r in the direction of a minus a2. Remember, a2 is the direction of minus h. So my angular velocity, let me stop sharing. Okay, so going back to this, I'm trying to compute the angular velocity of, this coordinate system that I've defined with respect to LVLH. Well, I do know that A3 and A1 are never changing plane, correct? And really, everything that is happening to this coordinate system is just a rotation about A2. Not constant angular velocity magnitude, because this is an elliptical orbit, so in general it may change. So that's why I gave you that expression, which is a function of r, of position as well. H is constant, but it's also a function of r. But if I look from, say, the point of view of h, I would basically see something like this. This is the planet. So I see, let's see, at some generic location, let's say down here, I will see A3 pointing that way, right, to the planet. This is Earth. And let's say that the orbit is going this way. So if the orbit is going this way, the angular momentum vector is pointing at us. It's coming out of the page. So A2 is actually going in because of how it's defined. Sorry, A2. Okay. And then, well, A1 is this way. So obviously the angular velocity for a problem like this, where it's a simple rotation about this axis, is a vector that it's going to point at us. It's a single axis rotation. Recall that the angular velocity in general is defined as that ugly skew symmetric matrix for a generic motion. But if we collapse everything to a single axis, then you can say that omega is the rate of change of an angle times the direction of that axis. And that's the case here. And the axis is A2 or minus A2. And so the omega of LVLH with respect to the inertial observer, if you like, it will be definitely in the direction of minus A2. And the norm of it changes. That's why it's inside the function that can update. It's H over R squared. Sorry. So it does change in magnitude, but it doesn't change in direction because this is a Keplerian orbit, and the plane of the orbit is just fixed in space. Now, in the code, again, all these vectors A1, 2, and 3 are expressed in ECI, and the same would be true for this angular velocity. Then it's expressed in ECI. So if I go back and share, that's all this function is doing. It's taking in position and velocity. It doesn't really use the velocity just because h is something that I have computed in my initialize file, but you could do it in here. It doesn't matter. But it takes the position and velocity. It takes the angular momentum vector. It takes the previously computed desired quaternion, and it generates the LVLH directions, A1, 2, and 3, the desired quaternion through this complex function here, shuffling the elements because of the way that this function works, while we are using quaternions where the scalar component is the last one, and then a desired angular velocity. So that's really the function that commands a desired trajectory. It's a trajectory attitude-wise, but still, nonetheless, a trajectory. So this is the function that is commanding what you want to do. And so that's all we need to say about this function. Now, this one instead takes the quaternion. This is coming from outside. So if I go back outside here, there is a block which is your Quaternion Kinematics. This probably sounds familiar. And so the quaternion goes in here. And let's see what we do here. This simply takes the quaternion of your body axis, and it puts it into a DCM form. And let's see what's happening here. I am multiplying the omega desired times this DCM. Any idea what this is doing? Any idea? So eventually we'll have to close the loop and control the satellite's orientation so that it follows the LVLH motion, right? But why am I taking these omega desired, and I am, before outputting it to whatever it's happening after the control logic, why am I pre-multiplying that times this inertia matrix? I'm sorry, not inertia matrix, DCM matrix. And I think the fact that I call it inertia to body is probably kind of an abuse here, but suggestions? So the equations that you're coding for homework 1, the kinetics block, those are, that's Euler's second law projected in which axis?
In the inertial frame.
Well, the equation is, we apply the transport theorem to get that form of the equation, right? Which means that the matrix of inertia is expressed in the body axis, right?
Yes, yes.
And so angular velocity as well. So everything there is in the body axis. And that's because, you know, practically speaking, as we discussed yesterday, you do have ways to measure your angular velocity with respect to ECI, of course, but it's projected in the body axis. Okay. So all I'm doing basically here is I'm taking the desired omega that I have expressed in ECI, because that's what we just discussed. The A1, A2, and E3, I built those vectors coming from the inertial position, the position vector of the satellite, which was expressed in ECI. So everything there is in ECI axis. And so if I want to use it probably for control purposes, it is convenient to project it into body axis. And so, oh yeah, now I remember why I call it inertia to body. So inertia is not the matrix of inertia. This means inertial. I should have put an L. So what this does is the DCM of the body of your spacecraft with respect to the inertial reference frame. So basically this multiplication takes the omega desired and just performs a change of coordinates. Now the omega desired that comes out after this multiplication is the still the omega desired. It's just that now it's projected on your spacecraft axis. Okay, that's what I'm doing. And then, as we will see, for the control law that we'll use, we also need the time derivative, the omega desired dot. So I have a derivative block in here, nothing more than that. I'll caution you, the use of the numerical derivation in software, it's usually a terrible thing to do. It's kind of a big no-no, unless it is a signal that you know it's not noisy and you can control. And in this case, that's what we have. So this is me taking the position of the satellite and operating on those vectors and creating these other quantities. So I know what they are, and I know they're not in principle measured other than R eventually, but that will be filtered. So it's not noisy signals that I'm feeding into the derivative. But in general, if you have noisy signals, things that are coming from sensors, for example, it's usually a bad idea to use derivative blocks and numerical derivatives. But in this case, it can be done, okay? But just keep it in mind that, you know, when I was working on my master's thesis, the one that I shared with you, I remember that I was insisting to take time derivatives of variables, and you know, I was cautioned not to do that, because in real life, you definitely don't want to take the derivative of a noisy signal and then use it for control purposes. It creates big problems. Okay, so this entire block here, this orbital mechanics block, is something that I strongly recommend you start working on, because the goal of this, I know it seems intimidating, but believe me, is not that bad once you break it down into the single components. The goal of this is creating the commanded attitude, the commanded orientation for your spacecraft. Orientation and angular velocity. They go together, of course. They're not completely disconnected. You can't really disconnect the desired omega from the desired orientation. In fact, we're not here. But I strongly recommend that you start working on this. So just keep in mind that your goal is integrating the Keplerian orbit with the initial conditions that I'm giving you here. I'll put it in a slide eventually. And once you have your orbit simulated, to create the desired quaternion and desired angular velocity as I have outlined, keep in mind that you have to use the function that I gave you, okay? The DCM2 quaternion mine, I called it, to create the Q desired and the omega desired. And keep in mind that you have to also, eventually you will have to change the projection axis of the omega desired, okay? So you see that things are starting to come together. Well, we covered astrodynamics today, so Kepler's dynamics should be a no-brainer. The function that I gave you is used in here. What else? Well, the DCM as a function of the quaternions, which is what you are coding for homework 1, will definitely be used for this operation here. So additional assignment to be performed as soon as possible is this. So you have this on video, look at it, and try to start working on it. And of course, for the time being, you don't have everything else in this huge Simulink model, but you have Quaternion simulated somewhere. You have these Quaternion kinematics, you're working on it, right? So you can definitely plug that in here. The omega in this case is coming from somewhere else, but in your case, you're simulating, a function with Euler's second law to generate omega. So you can absolutely do that. Normalizing here, what else am I doing here? Just normalizing manually. Well, another piece of this that maybe we can discuss, because now we've covered it, is the error quaternion. Remember we talked about error quaternion? Well, here it is. It's the rotation basically from, in this case, from your spacecraft to LDLH. It's the difference, even though here we're not really doing subtractions, but it's the difference between the orientation of your spacecraft, which is Q, and the desired one, which is Q desired. And it is in your slides, as we've seen, and it's just presented here in matrix form. But for now, you can just focus on the orbital mechanics block. Questions on these?
Professor, yes. I have a question, a suggestion. I mean, since at least for us from the school, we are tomorrow we are busy from essentially 11 a.m. to 7 p.m. apart from the lunch break. Maybe could we try to start working on this together tomorrow? Maybe in the morning, because at least most of us are still completing the first homework, so probably tomorrow morning we will do that, and it would be very useful to work together maybe on this.
Absolutely. So let's see, tomorrow I have, for me is between 6 a.m. and 8 a.m., 2 hours. For you guys is 11 to, no, what is it, 11 to 1? Yes, I think.
Yes.
Anyways, and then we have 3 more hours in the afternoon. So you're suggesting we dedicate the 2 hours in the morning to do homework 1 and this one, or the opposite, the afternoon? Which one is best?
I don't know. Yes, maybe in the morning.
Okay. Yeah, we can have those 2 hours without more theory and focusing on finishing the homework 1 and then building this component. Absolutely, we can do that. And then in the afternoon we'll switch gears and do something else. Yep.
Thank you very much.
Absolutely. The only thing that I would require is I would like one or two of you to share the screen and, you know, show what they're doing, and so that it's not just me opening and showing things that are already done. But yeah.
Sure.
Yeah. Any other questions? So you're starting to see that really you can't disconnect, you know, going back to this slide here, you really should never disconnect orbital mechanics from attitude mechanics and vice versa. A real spacecraft is an object that has a certain, you know, certain dimensions and sensors and devices. They need to be pointed in a certain direction, and that direction can only be defined if you know where you are on your orbit. So I'm really not a fan of separating orbital mechanics from attitude mechanics too much, but unfortunately that's what happens in most classes. But they need to go together. No more questions on these? Okay. So now we have a choice. We can kind of switch gears and talk about attitude, motion, stability, and gravity gradient. I know that these are topics that you were probably not expecting, but I think we are at a point where you have enough theory and assignments to work on that I don't want to push on topics that have to do with the final assignment, final homework. So this would be theory that is really not something I test you on, is not part of your assignment. But it's, I think, important material. So we have a choice to go through this, because we have another hour, or start deriving the equations of the momentum exchange devices, the ones that you have in your notes. I think we can take kind of a break from, so you have enough material to work. We'll do it in the morning as well for 2 hours, so we can just press on with these that are, you know, different topics, but absolutely I think important. What do you think? I guess that means yes.
Yes. Okay.
Not that you have a choice. No, you do. Okay, so let's see. I'm gonna start, and then we'll take another 5-minute break in a few. But yeah, so attitude, motion, stability, and gravity gradient to begin with, and then we can talk about other perturbations / useful torques. But, you know, it is important to study stability of any dynamics that, you know, that dynamics problem that we derive equations for. It's the first thing that we should do, actually. Study the stability of the motion under our examination. And so, you know that there are 2 ways mainly to stabilize a spacecraft. Do spin, dual spin, gravity gradient, aerodynamic, magnetic. Those are the passive ones, and then thrusters, MEDs, etc. for the active ones. But, you know, the one that would be really just studying the pure dynamics would be the passive ones. And because the first one, spin and dual spin, really have to do with just the motion itself. It's just the fact that you put your object into a certain RPM about one axis, and you see what happens. Is it stable? Are the equations of motion stable or not? Gravity gradient and the other effects, well, they're also just pure dynamics. If you think about it, it's not active control. You're not closing the loop. It's just that the equations become a little more complex, but it's just natural motion. While these ones are definitely, you know, there's a feedback control, and there's a lot more going on. But, you know, studying the stability of all those different approaches is important. So what is stability? Just a quick refresher. You know, a system is in general stable if after you give it a perturbation at a given time, whatever happens after that perturbation is an alteration of the unperturbed motion that remains bounded, basically. The oscillations with respect to the unperturbed motion are in the same order of magnitude of the perturbation itself. And that's simple stability if the oscillation remains constant, so you don't have any damping, basically. Or you have asymptotical stability, and you may have a way to actually cancel eventually out the perturbation, either by the dynamics itself that has damping in it, or because of something that you do. But so that's the more general, very high level definition of stability. If you want to, give a L stability here definition, well, the solution y, which is the trajectory given at a certain time t and given some initial conditions, is Lyapunov stable. This dynamic is Lyapunov stable if there is a delta greater than 0, such that for an epsilon greater than 0, one can maintain the delta y, the perturbation less than epsilon, for any time greater than the initial one by choosing any delta y0, basically the perturbation that is less than delta. So, but that's basically in form of, in a more formal way, what we just said. You give it a perturbation, in this case is a delta y0, and your trajectory will never exceed, in terms of oscillations, the amount of the given perturbation. It will not diverge, basically, from the unperturbed motion. And the system is asymptotically stable if, what we just said, after a perturbation, it will eventually, maybe in infinite time, but it will eventually actually go back to the unperturbed motion. And what really interests us for what I'm going to do next is that for a linear time invariant system, in the form that is here presented, x dot equal ax plus bu, we usually look just at the matrix A, and we say that the system is stable if all the eigenvalues of A have a real part less or equal to 0. So you can have some zeros, and that's simple stability. You can have only one zero, though, no multiple zeros. If you have more than one zero, then the system is unstable. And then you have asymptotical stability, which means that basically there is damping. If, can you still see me? I had a glitch on my screen. And
Yes.
I thought I lost connection. Yes. Okay. And if instead your eigenvalues have the real part that is strictly negative, so no zeros, then that means that you actually have damping capability, and so your system will eventually tend to the unperturbed motion. And these are things that I'm sure you know. What that means, by having discussed this slide, is that what is coming next is based on linearized equations, because I'm going to use the linear time invariant theory to study the stability of certain motions. Before we start, because when we look at some equations, do we want to take another quick break? Maybe 5 minutes? I just like to stop every hour or so, because I think, for me, talking for 2 hours straight is not ideal. And I'm sure that you guys can use a break every once in a while as well. Okay?
Okay, thanks.
Okay.
Yep.